is A greater than B, A equal to B, A less than B. 0, 0, what is the operation is? A equal to is 1, greater than and less than is 0. 0, 1 is nothing but what? A less than B is 1. This is 0, 0. 1, 0 means what? A greater than B. 1, 1 means what? A equal to B. So what is the relation you can see here? What is the relation? I can write A equal to B is nothing but what? A greater than B, NOR operation of A less than B. So 0 NOR with 0 means what? 1. 0 NOR with 1 is nothing but what? 0. 1 NOR with 0 means what? 0. 0 NOR with 0 is nothing but 1. I can write A, if I know greater than or equal or less than, I can find what? Equal. What is the relation is? NOR operation relation. What about A greater than B then? What is A greater than B is? A greater than B is nothing but A equal to B, NOR of A less than B. You can see 1, 0 is nothing but 0. 0, 1 is nothing but what? 0. 0, 0 is nothing but what? 1. 1, 0 is nothing but what? 0. You understand? Then what is A less than B relation? A equal to B, NOR of what? A greater than B. So 0, 1 is 0. 0, 0 is nothing but 1. 1, 0 is nothing but 0. 0, 1 is nothing but 0. This is a relation, NOR relation with the A greater than equal to less than. Are you understanding? Now in this circuit, I am getting C of is nothing but what? A greater than B. Now when you are checking the equal, what is equal operation is nothing but S3 is equal to 1, S2 is equal to 1, S1 is equal to 1 and S0 is equal to 1. For this, shall I take this through what operation? What operation? I want to check all these are 1 or not. AND operation. Correct. Now this gives me what? A equal to B. Are you clear? Then how to find out A less than B? I'm getting this. A greater than B. Here I'm getting what? A equal to B. How to get A less than B? What is the relation? A less than B is equal to what? A equal to B. Correct. NOR operation. Correct. NOR operation of what? A greater than B. So this gives me what? A less than B. Did you understand? So using full order, how you can make this as a what? Comparator. Now can you write a program to this using structural modeling? What is meant by structural modeling is nothing but use the half order to build the full order. Use the full order to what? Build the 4-bit full order. Use the 4-bit full order to build the what? Comparator. There is a structure in this, correct? Did you understand? Now can you write a program to this quickly? So what is the logic to checking for A less than B? What is the logic to check the A less than B? A greater than B, NOR operation is A equal to B. Two conditions. If Cout is equal to 0, correct, NOR of A equal to B, so that gives me Cout is equal to 0 also, that gives me what? A less than B. And to get the result of A less than B, do the NOR operation of equal and greater than. So how to get the A greater than B? How to get the A greater than B? Cout is equal to 3. If Cout is equal to 1, that gives me the A greater than B. Now can you write a program to this quickly? Using structural modeling technique. What I need to write first? Half order, right? Module, half order of what? Shall I write C and Cout, A comma B. So inputs are What is the input is? A comma B. Correct. Output is S comma C out. Then what I need to do? How to build the off order? XR gate 1 of what? XB. So this is sum, right? S comma A comma B. XR gate. Then AND gate of what? Gate 2. This is nothing but what? C out A comma B. So this then end the modeling. This is off order using gate level modeling technique. Now what I need to do? Module, full order. What is full order? Outputs are sum comma C out comma A comma B comma C. Next one. Input. What are the inputs are? Input are A comma B comma C. Output are S comma C. Right. Then what I need to do? I need to do. We need to instantiate the off order. Off order, correct. Gate name. Let us make this is gate 3. Of what I need to write? Yes. How many off orders are required to build the full order? 2 off orders, correct? This is a circuit, right? XR. Again, this will be XR with what? CI. This is the sum. This is AB, CI. What is carry is? A and B. A and B. Again, this is AND with this, correct? Sorry. This is AND with this. And these two are again, if you use the OR operation, the XOR operation, no. This is a carry. This is one off order. Off order 1. This is what? Off order. Now to instantiate this, already I have designed the off order. Correct? How to design the full order is? Shall I take this is W1? Correct? This is W2. This is nothing but W3. So one off order, what are the output is? W1 comma A comma B. Then so how to instantiate this one?
दो ले इधर खत्म कर दे फटाफट और एक सेव भी ले ले पहले
Off order. So if I write W1 comma A comma B, that is for XR, right? Off order, how many inputs will be there? 2 inputs. How many outputs will be there? 2 outputs. How to instantiate this? Okay. W1 comma W1 comma W2 comma A comma B. Correct. Next, off order, gate 4 of what? You can see this diagram. Sum comma W3 comma W1 comma CI. Correct. So sum comma means S comma is S comma S comma W 3 comma W1 comma C. Next, I'm using XOR here, or you can use OR gate also. Nothing to it. XOR. Let us take gate 5 of C out. Okay. Comma W2 comma W3. Correct. This is W2 comma W3. This is XOR. Now let us do one thing. Write the test bench to this and check the working of this. Okay.
कोई आएगा
So
क्या
module TV rich A comma B comma CI, then void S comma CO. Next, what I need to do? FA DUT. So let me go with connection by default. Okay. Here initial begin. So A comma B comma CI is equal to what? Dollar symbol random. Let me introduce some delay here. Then let us display. Display of what? A is equal to percentage B, comma B is equal to percentage B, comma CI is equal to percentage B, comma S is equal to percentage B, comma C out is equal to percentage B. What are the argument is A comma B comma CI comma S comma C out. Correct? Then what I need to do? End the model. Are you understanding? Now let us run this code. 1 0 0 sum is 1, carry is 0. It is working fine. Now what we can do? I want to check exactly, so that I am going to repeat this for 10 times. Then I am going to end this. 1 0 0 sum is 1, COT is 0. 0 0 1 is sum is 1. 0 0 1 sum is 1. 0 1 1. Okay, this is working fine. Let us copy this. 1 0 0 sum 1 0. 0 0 1 is sum 1. 0 0 1 is sum 1. 0 1 is sum 1 is carry 0. 0 1 0 is carries 1. Carries 1 carries 1. Sum is 1 sum is 1 carries 1. Now this is working fine. Okay. Now let me pull down this. This test bench I am going to pull down. Let me give comment to this test bench. Now we have done with what? Full adder. Now what I need to do? 4-bit parallel adder. So full adder 4 of what? A comma B comma CI comma S comma CO. Here inputs is nothing but one. Input is 3 down to 0, right? Parallel ladder I am designing. This is 3 down to 0, A comma B. Again input, correct, CI, then output 3 down to 0, yes, then output C out. Correct? Next, what I need to do? I need to instantiate. This is full order. Let us take gate 6 of what? What I want to instantiate here. What is full order? Output is nothing but S of 0, correct? Comma A of 0, correct? What are inputs to the first full order is? A0, B0, CI, then what are the output is? S of 0 and C of 0. Now we need to declare the void data type here. Correct. The Y data type is what? Shall I declare this as C0, C1, C2? Correct? Did you understand this one? Now what I need to write here? A of 0, comma, B of 0, comma what? CA. How do you understand? Carry is also there, right? This is nothing but what? C of 0, comma. Yeah, this should be C0. If I am declaring wire is 3 down to 0, then it is C of 0. So let us write like that. This is 3 down to, how many down to 0 we need? 2 down to 0 we need. 2 down to 0, then C, then I am going to write this is nothing but what? C of 0. This is A of 0, B of 0 and CA. Next is what? Again, we need to instantiate full order, right? Again, full order. This is gate 7. Then S of 1, C of 1, A of 1, E of 1. Then this is C of 0. Right? Then next is what? Again, this is gate A. S of 2, C of 2, A of 2, B of 2, C of. Next one. Gate 9. This is S of 3, C out. This is nothing but C out. C out, A of 3, B of 3. This is nothing but P of. And what I need to do? In the one. In the. Now let us check for syntax sense.
Wait, no stop. Oh my god.
Now, shall I modify the same test bench to check with what? Parallel ladder. So, what is a parallel ladder? Now, what I need to do here? Okay, write the test bench to this now. Module TB, reg 3 down to 0, correct? 3 down to 0, A comma B comma C. Sorry, A comma B. Then this is reg CA. Then this is Y is 3 down to 0 of yes. Then Y C out. So I need to instantiate what? This full order 4. Now here, okay, let me give the same. No worry, right? A comma B comma CI dollar symbol random. So now A is 4 bit, B is 4 bit, C is 1 bit, sum is 4 bit, C out is 1 bit. So I can use the same test bench. Now let me remove this lines. Okay. Now let us run this code. So let me print this in the decimal so that you can understand what is the additional decimal. Now 9 plus 2 is 11. Correct? You are able to see this. Let us copy this one. You can see this. 9 plus 2 is 11. So 4 plus 1 is 5. 4 plus 1 is 5. So 3 plus 1 plus 1 is nothing but 5. So 8 plus 6 is nothing but 14. 14 plus 1 is 15. So 12 plus 6 is 18. 18 plus 1 is 19. So that AC3 CO2 is 1. Here 0 plus 9 is 9. So 8 plus 1 is 9. So 8 plus 6 is 14 plus 1 is nothing but 15. Now this is working as a order. What order? 4 bit full order. Correct. Now let us come into this. Now our intention is to design what? Compare. Now we need to design here. We need to design what? Design or implement the 4 bit comparator, 4 bit comparator using 4 bit full order using structural modeling technique. So how to write this? Module, correct? What is the module name? Shall I use means comparative? So what are the menu entries? How many inputs will be there? 4-bit input menu and 4-bit subtrahend. So shall I take A comma B and A greater than B, A less than B? Let us write A equal to B, A less than B. Then here input are what? Input are 3 down to 0. Shall I take the vector A comma B? Then output are what? A greater than B, A equal to B, A less than B. Now what I need to do? I need to instantiate what? Full order 4. So shall I take this is gate return, name of this instance. Now what I need to write here? What I need to write? I need to check for A greater than B, then A less than B, then A equal to B. So first we'll write it for A greater than B. What is the condition for A greater than B is inputs are A0, A1, A2, A3, correct? And subtrahands are what we are doing here, complementing. Means I should take a inverter, bitwise inverter, correct? Then what is C out is nothing but my A greater than B. This is my sum. Did you understand? This is my sum. So how to instantiate for A greater than B now here? S is 4-bit, S comma. C out is nothing but what? A greater than B. C out is A greater than B. Then A, this is a menu end, 4-bit menu end. What is subtrahend is? Negation. This is a negation, right? Total means we are taking the complements of B. Then what I need to do? CA initially I can pass. So 1 tick B 0. CA is equal to 0 I am making for this. Here I am making this CA is equal to what? 0. 1 tick B 0. For this parallel order. This is A3, A2, A1, A0. And this NOT gate I am representing using what? Fiddle. So B0, B1, B2, B3. Means B0 bar, B2 bar, B3 bar, B2 bar, B1 bar and B0 bar. And this C out I am taking as what? A greater than B. This is my 4-bit sum. S0, S1, S2, S3. What is my C in is nothing but? C in means CI. C is nothing but 0. So this is the one. Correct? So this gives me what? A greater than B. Then how to check the equal? How to check the equal? You need a what gate? AND gate. How many input AND gate? 4 input AND gate. Correct? What is the output of this gate is? A equal to B. Input is, so shall I use AND gate? AND of, so G11 of what? A equal to B, comma, S of 3, correct? Comma, S of 2, comma, S of 1, comma, S of 0. Did you understand? These were equal. Then how to check the less than? NOR gate. NOR of what? Gate 12. Of what is this is nothing but. Output is A less than B. Input is what? A greater than B, comma, A equal to B. For A less than B, what is A less than B? A greater than B and what? A equal to B. What operation? NOR operation. Did you understand this? Now what I need to do? I need to end the. Now let us check for the syntax error. So it is showing that port 1 of A, full order 4. So I am declaring this as how many bits? Line number 41. This is what I am declaring right here. Output, sorry. Here I am writing port connection is not correct. Right? Correct. Wide of what? Read down to 0. Yes. Now this is working fine. Because I'm taking this as wide data type. This is not S1, S2, S3. Now, did you understand this? Now let us write the test bench to this. What is the test bench to this? Module TB, correct? I'm using A comma B. So do you need this? No. I'm going to remove this. And what are the wide data type is? The wide data type is A greater than B, correct? A equal to B, A less than B. In this. Now what I need to do? I need to instantiate the comparator UT. So let us go this by, okay, default, let it be. Then what I need to do? I need to generate the A and B value. Then here I don't need this. I'm going to remove this one. So what I need? A greater than B, right? Next is A equal to B. Next is comma A less than B. A less than B is equal to dollar symbol B. Now what are the argument I need to pass to this is AB, A equal to A greater than B, A equal to B, A less than B. Correct? And these are the same. I'm repeating this for 10 times. Then here I'm using dollar symbol random, I'm generating A and B. Then I'm giving the delay. Then I'm printing the value, displaying the value. Then I'm going to end the module. Is it clear? Now let us run this. Now let us copy this. Now we can analyze the output. A is 2, B is 4. Means what? A is less than B is 2. A is 8, B is 1. A greater than B. A is 0, B is 9. A less than B. 6, 3 greater than 0, 13 less than 8, 13 less than 6, 15 greater than, correct? 1, 2 less than 0, 1 is less than 0, 13 is less than. So, but in this case, it is not checking with what? Equal condition. Let us do one thing. Let us assign port tick to B. Let us give 1, 0, 0, 3. Now A is also what? Is it 4 tick to B? I should give what? 8 tick to B, right? Because I am concatenating it. 8 tick B 0 of 1. 1, 0, 0. Now B will take 1, 0, 0, 0. A will take what? 1, 0, 0, 0. Now A and B are equal in this case. So A and B are equal. But I am repeating how many times? 10 times this. So that this is printing how many times? 10 times. Now A is equal to 8. B is equal to 8. This is nothing but what? A is equal to B. How do you understand this program? So let us remove this. Let us give the dollar symbol run. Very clear? So how to do structural modeling technique? For this program, what basically we have done is, so we have done the full ladder using what? Half ladder. Parallel ladder using full ladder. Use the full ladder to design the what? Comparator. What is the logic to design the comparator using parallel ladder? What is the logic to comparing the two numbers, right? You are taking the subprime using complements. Then if C out is equal to 1, you are saying that your A is always A is greater than. If C out is equal to 0, A less than A. If your sum bits are what? 1, 1, 1. That is what? Equal. You can understand. So using this, we are building, using the parallel ladder, we are building the 4-bit comparator. I hope this is clear. Okay, with this we'll be stop the gate level modeling technique. Okay, so we work the examples on gate level modeling technique, like flip-flops, counters, and then some combinational logic circuit. So someone will gives you the diagram or digital diagram. You can able to write the gate level modeling technique. So now we'll begin with the very high level modeling technique is nothing but behavioral modeling technique. So the next level of abstraction we are going to discuss about is nothing but behavioral. Behavioral modeling. So this we call it as a high level of abstraction. So you don't require a what? If you remember, what are the level of abstractions? Switch level, gate level, data flow. Now we are coming to the high level. To write the switch level, what knowledge is required to do the switch level modeling technique? So we need a CMOS transistor level operation. Okay. So coming to the gate level, using logic gates, using primitive logic gates, you are instantiating that and then you are building the logic, writing a program. Then what is another level is nothing but data flow. How data is flowing through the registers. Using that means the level of abstraction you are using is nothing but a Boolean expression. Using Boolean expression. So we are writing the data flow modeling techniques. Now very high level of abstraction we call it as the behavioral modeling technique. So this technique or modeling, behavioral modeling technique is also called as algorithm manner technique. Algorithm manner technique. So you don't require a gates, primitive gates. You don't require a logical equations, Boolean equations. You are representing the manner. The mannerism you are representing, behavior of the circuit you are representing as a text form. That modeling technique we call it as a behavioral modeling technique. Let us take one example to the behavioral modeling technique. If you talk about counter, how you can do in the data flow modeling technique? Counter. How to do using data flow modeling technique? Say for example, 4-bit asynchronous counter. 4-bit asynchronous counter. How to do this? Let us take gate level modeling technique. How to do this? So asynchronous counter is how many flip-flops are required? 4 flip-flops are required. So this is the clocking nature. Output of each flip-flop is feeding clock to the next flip-flop. And this is nothing but what? Toggling flip-flop. This toggling flip-flop design using what? D flip-flop. You can understand nectar is receiving D flip-flop. So that you are converting into what? T flip-flop. Use the T flip-flop to design the 4-bit counter. Are you understand? Suppose I am asking you to write a Verilog program for traffic light control. You have any equations, exact formulas, any exact equations? Is there for this traffic light controller? No. 4-bit parallel ladder, counter, 4-bit asynchronous counter, you know what is a behavior. 0, 0, 0, 0, 0, 0, 1. 2, 3, 4, 5, so on. You know the background, what flip-flops are used to build this. So when you talk about counter, whether it is asynchronous counter or a synchronous counter. If I'm talking about traffic light controller, I don't have any logical equations for this. Correct? Exactly. I don't have any logical equations to build a traffic light controller. So this traffic light controller can be built using algorithmic manner. I know behavior of that circuit. The behavior of that circuit is, suppose red color is glows for what? 60 seconds. Yellow is glowing for 10 seconds. Then then green is glowing for, let us take 60 seconds. I know what is that behavior. Using that behavior, you are going to write the high level of abstraction. Or you understand? So that level of abstractions we call it as a behavioral modeling technique. So the behavioral modeling technique is more flexible than all your other level of abstractions. So you are writing a English text using control statements like conditional statements, then looping statements, then multi-branching statements, means case statements. Using this, you are going to modeling the level of abstraction. That level of abstraction we call it the behavioral modeling. It is more flexible than all other modeling techniques. So developing algorithm manner, you are writing a English text. Let us take very simple example. This counter to design how many lines of code we are doing in the gate level. Asynchronous counter. We are writing for negative H degree flip-flop. Then that will be converted into a T flip-flop. Then we are instantiating that T flip-flop to build a one. 4-bit magnitude, 4-bit counter, asynchronous counter. Now, in your behavioral modeling technique, you can do within 2 lines. So, what is the basic building block for this is nothing but always. Data flow, what is the basic building block is nothing but assign. Gate level, what is the basic building blocks is using primitive gates. So, always you are writing at the rate of, this is nothing but event. We'll talk about this event. So, you are saying that always at the pass edge of the clock. You are doing that, Q is equal to Q plus Q. That's it. Whenever pass edge comes, you are incrementing the value of Q. So before that, you are initializing Q is equal to 0. Q is equal to 0. Whenever rising edge of the clock comes, what happens here? Count getting incremented. Means up counter means what? 0, 1, right? So at the first clock, it is 0. Whenever it will remain same until the next rising edge comes. When the next rising edge comes, you are incrementing the count by 1. Right? Count 1, count 2, count 3. So I can do within 2 lines of the code. So that it is allowing user for more flexible way of designing the model, designing any hardware circuits. Are you clear? So this level of behavioral modeling technique is nothing but a high level of abstraction. You are writing a English text to model in the hardware. Are you understand? So we will discuss this in the next session. We'll start with what are the structural statements are there, initial and begin. What is the difference between initial and begin? Then we'll talk about the procedural statements, means blocking statement and non-blocking statements. And also we'll see that how delays are introduced. The delays are introduced in where? Specified in the gate level modeling technique and then primitive gates, data flow modeling techniques. We'll see how you can define the delays, what are the various delays are used in the behavioral modeling technique. So next session we'll start the detail about behavioral modeling techniques. So these are one of the high level modeling abstracts. So with this, let me stop the session here. So we'll continue the next session with the 4th level of abstraction is behavioral modeling. So there we're going to discuss about control statements like if else statements, then multi-branching statements like case, K6 and KZ. And then we'll talk about loops like a repeat loop, forever loop, for loop, while loop. Then we'll see what is the difference between initial and always, how initial works, how always works. Okay, what is the basic building block for the behavioral modeling technique. We'll see some of the concepts like blocking and non-blocking, what is the use of blocking and non-blocking, with delays. So all this we'll discuss from the next session. Yeah. I request online students to fill the attendance now. So any questions are there, you can go ahead now. I request online students to fill the attendance.
Okay, sir.
Okay, let us stop this session here. So we'll continue in the next session.